It's a great honor to speak here at this conference for the birthday of Richard Stanley. In particular, so because neither have I been a student, nor a postdoc, nor a collaborator. But I believe that in a sense, I'm a distance learning student, which probably applies to everybody who has not been directly a student, postdoc, or collaborator. So my PhD thesis was on Q-Lagrange inversion. Sorry, this is not a legacy of Richard. And then, after that, for some reason, I became very much interested in plane partitions, enumeration of plane partitions. And as opposed to George Andrews, I have no idea how this happened, but it did happen. And then, if you become interested in the theory of plane partitions, there are certain musts that you have to look at. Here is one thing. It's a two-part paper. It's a survey paper on the symmetry classes of plane partitions. And it's from the year 1986. And there's another paper from the year 1986, where Richard presents 13 conjectures. Here the title is a bit misleading, not only on plane partitions, but also on alternating sign matrices. And I'm very sorry to tell that I couldn't solve any of these conjectures. But at least a former student of mine, Denise Fischer, together with Roger Behrendt and Matthias Konvalinka was able to solve one of these conjectures. But even earlier, there's this 1971 two-part paper of Richard, where he explains that if you do enumeration of plane partitions, then you should look at them from the point of view of symmetric functions. And I believe this is a very early version of chapter 7 of his second volume of enumerative combinatorics. And what he preaches there is apply symmetric functions to solve plane partition enumeration problems. And indeed, he follows this advice in this paper, where he solves the enumeration of self-complementary plane partitions by showing that if you lift things on the level of Schur functions, then what you need is a very beautiful instance of the Littlewood Richardson group. Right, and so this advice, use symmetric functions. When you do plane partition, tableau enumeration, this is what will become important in my talk, which is joint work with Ji-Sung Ho, Shang-Soo Kim, and Suichiro Okada, who is sitting here in the second row. So the starting point of all this is an enumeration result by Mortimer and Prellberg, which somehow looked very isolated. I will not explain it. Essentially, what it says is that a certain number of arcs in a triangle is the same as the number of Motzkin paths which are constrained to a strip. And the goal of my Korean colleagues was to find a bijective proof of this result, because Mortimer and Prellberg, what they did is that they computed the generating functions on both sides, and so, oh, it's the same, and therefore it's the result, but it doesn't explain the result. Okay, very good. Right. So what my Korean colleagues did is they translated this result into something which is equivalent. Namely, so just to remind you, on the left-hand side you have Tn of something, and on the right-hand side you have mod n of something. The left-hand side is paths on the left-hand side are in bijection with certain standard Young tableau. They have size n, 3 rows, And then there is a funny condition, a kind of cylindric condition. This refers to my title. Namely, the difference of the length of the first row and the length of the third row, last row, is at most another parameter m.
So the refinement of the record, right?
I don't think so.
I mean, the record goes with the number of, what's the number of stands comfortable.
Yeah, no, this is not. This is not.
It looks like refinement.
It is a refinement. Yeah, yes. So I give you an example. So here's a standard Young tableau, and I hope that everybody knows here what the standard Young tableau is. Otherwise, you shouldn't have passed the entrance exam to this. Right, so n is 9, so these are it's a standard Young tableau of size 9. And the difference of the length of the first row minus length of the last row is at most 5. So right, I forgot to say something. When you consider any of the sub-rows formed by the first few entries. So if you take the whole thing, then this difference is 5 minus 2 is 3. This is not yet 5. Then if you look at the entries from 1 to 8, then now the difference is 4. If we look at the entries from 1 to 7, difference of this row minus this one, which has become 0, is 5. So this condition is still met, and then from here on, of course, the difference can't be more than 5. Correct. Okay, this was the left-hand side. For the right-hand side, it's not difficult to show that these Motzkin paths are in bijection with certain matchings. Namely, matchings without a 2 crossing and without an h+1 crossing. We have this h. So what do I mean by a matching? By matching, I mean a partial matching. It's not a complete matching, but a partial matching of 1 up to n. And then what is a k crossing? The k crossing is k matching arcs such that any two of them intersect. This is a k crossing, and then k nesting, this suggests itself. If you have k arcs where the first is inside the next and the next is inside next, this is a k nesting. What we have here is matchings of 1 up to n without a 2 crossing and without an h+1 crossing. So let me denote this standard Young more generally. This standard Young tableau of size n with at most h rows, and on this funny cylindric condition W by the symbol SYT sub n HW, and let me denote by NCNN sub n RS the set of R non-crossing and S non-nesting matchings on 1, 2 up to n. Then the things that I've explained to you now imply that if you believe into the results by Mortimer and Feldberg, then you have this equality. The standard Young tableau with parameters 3, 2, W plus 1. They are as many as matchings without a 2 crossing, without a W plus 1 crossing. And then my Korean colleagues told themselves, maybe this is part of a family. Maybe SYT with parameters 2h plus 1, 2, W plus 1 is equal to NCNN with parameters h plus 1, W plus 1. And now it's completely symmetric. And this is what they sent me. So they said, we believe that this is true, but we are not able to prove it.
This number L, C, and M, symmetric, S and T.
Yeah. Yeah, this is one of the fundamental results of the paper of Richard with many comments. From the definition, it's not obvious, but this is other questions. Okay, then. So I got this. First, I didn't believe it because it's so strange. In particular, this relative width condition is very strange. But I went to the computer and then I believed it quickly. How do you prove it? How do you prove it? But one thing that I could see, namely, I could find a formula for the left-hand side and for the right-hand side. And I briefly explain this. So for the left-hand side, this standard Young tableau, it's very easy to see that they can be translated into paths in 2h plus 1 dimensional space. So lattice paths, and they consist of positive unit steps in coordinate directions, and they stay in this region that you see here. Specialists will see that there's this, the coordinates are in order, but then there is also a relation between the last coordinate and the first coordinate. So there's this cylindric condition again. So this is a scaled Arco of type A. And then there is a formula for these paths if you start at 0 and fix the end point, which is due to microphyllaceta. And it turns out that it's a special case of the binary chamber formula of Stanley. And here's the formula if you fix the end point. And then the only thing that you have to do is you have to sum over all possible endpoints, and you have a formula for the left-hand side. It's a bit complicated, that's true. We have to sum over partitions. So this symbol here, I have to put this here, means lambda is a partition of n. And this is a multiple summation, but still it's a formula. So what about the right-hand side? The matchings, they are in bijection with what is called alternating tableau. So again, these can be interpreted as certain paths. The bijection is described in the paper by Richard and many authors. So again, you can translate this into certain paths which stay in an L-curve of time C now. And again, there is the formula of Stanley, and thus you get a formula for this. It's again a complicated formula. If it's sum over m, and then you take the coefficient of this term in this expansion, and the i's, these are modified special functions, but still it's an explicit formula. Is there a question? Okay. So to summarize so far, this conjecture between numbers of standard Young tableau and numbers of matchings is equivalent to this very nice identity. But of course, how do you prove this identity? I didn't know. I sent it to my Korean colleagues. And actually, I made another observation, and now comes the important lesson. So there's an important principle. Whenever you don't know how to prove something, make it more general. Maybe this is easier. That's folklore. Everybody knows this here. But we need a special case of this. So today. That's a special case. The question? Whenever you encounter an identity, yeah, there's a question, please.
No, I was just amusing that you started by saying generalized things and then make a special case.
Good point. Right. When you encounter an identity which is related to standard Young tableau, then there should be a symmetric function identity behind. This is exactly what Richard preaches in this article. And this is what helps here. And I want to be more specific. So I need the elementary symmetric functions. And then whenever you see a multinomial coefficient, then this is really a product of elementary symmetric function where you take a particular coefficient. More precisely, if you have this multinomial coefficient, so what I'm assuming here without saying is that the sum of the mi's is equal to n, then this is equal to the coefficient of x1, x2 up to xn in this product of elementary symmetric functions. Right. So if we go back to our formula, we can apply this here and just point out one term. So if you imagine that you extend the determinant according to its definition, it's the sum of the permutation, sign of the permutation, and then product of corresponding entries. You multiply such a term by n factorial, then you will quickly see this is a multinomial coefficient. Therefore, you can apply this rule if you want. And you arrive at this expression. The previous formula comes about if you extract the coefficient of x1, x2 up to xn on the left-hand side, on the right-hand side. Of course, there is no guarantee that this is an identity, but you go to the computer and you observe, well, it works out. Okay, very good.
Why do you even need a proof then?
Noron should have. He accuses me. Oh, I don't. Oh, when it turns to that, it's up to degree 20, I think.
Yeah. Well, then you don't need.
Okay, and then when you are there, then you become greedy. So, for example, there's 2w plus 1, and you can also see 2w plus 1 in there. Maybe you can replace 2w plus 1 by w. Still works. What I've done here. Still works. And then, of course, you will observe there's also 2h plus 1. But this is not so easy because so what you think is true is not true, but there is a companion identity where instead of 2h plus 1, you have 2h here. And then the right-hand side is also a bit different. You see here is the minus. Then for the companion identity, you have a plus. And actually, this is what I put into the computer first. And that did not work until I observed that I had to put in the sign. Okay. So, of course, we still don't have any proofs, right? But what we observed is that there's a special case of this, which is very well known. Namely, when you send W to infinity, so you have to think for a moment, then the thing only makes sense if none of the ki's is non-zero. Any of the ki's is non-zero, then you can forget the terms. That is, if you send W to infinity, then only in this sum and also in this sum, the terms where the ki's are equal to 0 remain. So here's the first identity where I send W to infinity, and you get this summation here. It's a summation of lambda of certain determinants of elementary symmetric function, and it's expressed again in terms of a determinant where these f functions are sums of products of elementary symmetric functions. this identity is a very well-known identity for Schur functions. So this determinant here is a Schur function, and so this identity is equivalent to this summation formula for Schur functions. I have also explanation about Schur functions, but again, I don't think it's necessary. So it's the sum over semi of monomials corresponding to semi-standard tableau of that shape. And so the first identity and it becomes this one, the second, here it is again, right? And then the second identity has a similar interpretation. So it's again sum of Schur functions. Now the lambda 1 is bounded by 2h. Earlier it was bounded by 2h plus 1, and it's again expressed in terms of a determinant. And these two identities play an important role in the theory of enumeration of plane partitions, and also in the representation theory of GLN and SLN. And this now gives a hint how to prove these conjectures. Namely, how does one prove the Schur function summation? Well, in the first step, you apply the minor summation formula of Ishikawa and Wakayama, because it turns out that this formula is applicable to this sum of Schur functions. The second step, you use an identity of Gordon to reduce the determinant that you get, the Pfaffian that you get, to a determinant of half the size. And in the third step, you apply certain row and column manipulations until you arrive at the result. This procedure is very well described in John Stanley's paper on plane partitions and non-intersecting lattice paths. So how does one prove our conjectures? There's a preparatory step where you do some arrangements of the terms in our biggest summation, and then you realize that the minor summation formula can be applied again. Then you use Gordon's reduction from the Pfaffian to determinant, and you apply exactly the same manipulations of rows and columns as in Stanley's paper to get the result. Right, so here's the first identity. Now it's proved. For the second identity, it's exactly the same. Of course, so we started with something combinatorial, and then we went into symmetric functions, and this is where we ended up. And as I explained, if you extract the coefficient of x1 times x2 up to xn, the left-hand side, right-hand side, then you get this speculation. That was the starting point, and in particular also the identity of Mortimer-Fellberg. But of course, there's still no bijection, and we didn't find a bijection. There were other authors who found a bijection for the result of Mortimer-Fellberg, but we were not able to. But instead, we found something that is much more general, namely this identity and the companion identity. But the question is, does this have a combinatorial interpretation? And so since time is running out, so yes, there is one. If you extract the coefficient of x to the m, this is multi-index notation in the left-hand side, then this equals the number of cylindric semi-standard tableaus. So there's again such a cylindric condition with at most 8 columns, and now it's a relative height which is restricted by W. Alternatively, you can also formulate this in terms of certain lattice paths that are bound to this scaling alcove of type A. And this follows from the theorem of cylindric partitions from paper that I wrote many years ago with Ira Gessel. As a matter of fact, if you pixel so you forget about this outer sum here, just look at this. This appears in work of Bosnikov, Schubert calculus, and he calls it cylindric Schur polynomial. And it also appears in the paper of Cooper and Wenzel in the Hecke algebra. So this is the cylindric Schur function from the type. And the right-hand side is also a combinatorial interpretation in terms of certain up-down tableau. And then again, you have an equality of, on the one hand, semi-standard tableau with the cylindric completion and this up-down tableau, but still no bijection. I believe it's very hard to find a bijection. The open question is, since I explained to you that this is something that does appear in representation theory, whether there is a representation theoretic meaning of this identity, I don't know it. And so I leave you with that question. And I thank Richard for all the support he has given to me over the years. And happy birthday.